Be grueling, but let's try to keep more or less on schedule, at least for the next talk. It's pleasure to welcome Alexander Engel to the conference, who'll speak on propagation of operators and uniform row algebras.
Okay, so thanks for the introduction and also for the invitation to speak here. So let me start with some basic motivation from physics before I start with the mathematics. So the following arises usually, or I don't know if it's usually, but it arises in solid state physics, topological phases, and so on. So we start with a space X and we discretize the space. Then we put a finite dimensional vector space over each lattice point. And then we consider Hamiltonians that close by points interact with each other. As you hopefully see in this small picture that I have here on the bottom of the slide. So the dots are the discretization of the space X, and then you have a Hamiltonian which lets them interact with each other. And so usually then we are interested in the spectrum of these Hamiltonians or in its resolvence and so on. And one feature that these Hamiltonians usually have is that only particles at the finite range can interact with each other. So in the sense that there's a bound on the range between the particles which interact with each other. So let us just put this together into a definition. So we have a metric space X, and we have this normed vector space V, which we will put above each point of X. And let me denote by P of X the projection onto the copy of this vector space V, which is sitting above the point X. And then we have a bounded linear operator T acting on the square summable sequences over X. And we say this operator has finite propagation if there's a number R such that Px after T after Py is 0 for all points X and Y which are further apart than R from each other. So this is just a formalization of the physical fact here. If you say that there's a bound on the distance between points which interact with each other. So basically the operator T resembles this interaction, and finite propagation means that there's this bound on the distance of interacting particles. So what we can also do to if you want a picture of this operator T, which is somehow nice to have in your mind, is you can write T actually as an infinite X times X matrix, so a matrix whose rows and columns are indexed by the points of X. And then having finite propagation just means that the matrix you got is band diagonal. So in this picture, so if your bound is R, like in the definition, then the diameter of this band will be 2R because you can go in both directions in this band. And actually, if you search around for band diagonal matrices, then you also find a lot of literature about this, which actually does not have much to do with physics, I think, but with applied mathematics and things like this. So band diagonal matrices are also studied a lot. And that's basically what we're going to do in this talk, studying band diagonal matrices indexed over space X. And now what we want to do is just to put all these operators together into one gadget, namely a C-star algebra. So we just define the uniform row algebra to be the closure of all finite propagation operators. And taking closure means we take it with respect to the operator norm, so inside the bounded operators on A2 of X. So this will be by definition a C-star algebra, because we have taken the closure and operator norm. And of course, what you have to check, but it's of course clear that that's compatible with the forming adjoints. Because if you have a band diagonal matrix, you form the adjoint, it's still band diagonal. So for simplicity in this talk, we just consider the case of V being the complex numbers. And we just write C star U of X for the corresponding uniform row algebra. So that's an invariant that you attach to an arbitrary metric space. Or for example, usually what I do is then to pass to the K-theory of this. But this is something fundamental that you can do with the metric space because it encodes in a fundamental way the metric of the space. And now if you wonder why this stuff is called uniform row algebra, where there's of course also the usual row algebra, that's a variant of this. Namely, in this case, you use as your vector space V in infinite dimensional separable Hilbert space. But then you have to additionally demand one further property. Then you don't just consider the finite propagation operators, but you demand them to be locally compact. And locally compact here means that the matrix entries are compact operators. So the matrix entries in this picture here. And if you close this up in operator norm, then you get what is usually called a row algebra. But so for simplicity here in this talk, I will just consider the uniform row algebra because then I don't have to take care of the compact entries and so on, just to make things here in the talk easier. And the two main questions that I want to address in this talk about this uniform algebra are the following ones. So the first one is which operators are actually in the uniform row algebra? Because by definition, let me go back, we have taken the closure and operator norm. So in general, an operator in the uniform row algebra has infinite propagation. So it's an infinitely sized matrix. I mean, the entries are everywhere in the matrix. And the question is, can you somehow read off from the entries somehow if such a matrix is in the row algebra or not? So that's in general an extremely hard problem. So if your matrix is not band diagonal, then to figure out if it's actually in the uniform row algebra or not, that's a very hard problem. So yeah, so that's the first question. What kind of operators do we get by forming the closure? And the second question is, what can we say in general about the resolvence of the finite propagation operators? So this is maybe again a bit motivated by the physics here. If you consider the Hamiltonians as sitting inside the uniform row algebra, so having finite propagation, and then you're interested in the spectrum of them, you want to compute the resolvence. What can you in general say about these resolvents? And we will see in this talk that answers to both questions, they are based on one notion, which I'm going to introduce now, namely the quasi-local operators. But before I do this, I introduce bounded geometry, as I see. So bounded geometry, means the following. So we have a metric space X, and we say it has bounded geometry if for every number R, this supremum that you see here is less than infinity. So what do we do here? We go through all balls of radius R in our space, and we just count the number of points in these balls. And we want that this is just bounded independently of the point X. But of course, it depends on R, but the bound is independent of X. So especially if a space X has bounded geometry, then it's discrete, right? Because in every ball, you only have a finite number of points. So this means that here for this definition, we have already passed to a discretization of our space. So very basic examples. So the first one, of course, if you look at the lattice Z to the N inside R to the N, then it has bounded geometry, obviously. But you can actually generalize this, namely, if you have a Riemannian manifold, which has bounded geometry in the Riemannian manifold sense. So this is what the footnote here explains. So bounded geometry in the Riemannian manifold sense means that the injectivity radius is uniformly positive and the Riemannian curvature tensor is uniformly bounded. So for example, every universal covering space or every covering space of a closed manifold with the pulled back metric has bounded geometry. Then if you have such a Riemannian manifold, then you can consider any maximal epsilon separated subset in it. And this maximal epsilon separated subset will have bounded geometry as defined above here on this slide. And it's just a direct generalization of the first example because this lattice C to the N, it's the maximal one separated subset in R to the N, which has bounded geometry as a manifold. So this means that basically there are enough spaces of bounded geometry that we care about. And maybe I should note here, I have not written it down on the slides, but so what happens if you have a Riemannian manifold given and you choose two different maximal epsilon separated subsets? Then you can form different uniform row algebras, namely with respect to the two different subsets that you have chosen. But what you can do is you can show that in this case, the uniform row algebras that you get will be Morita equivalent and hence have the same K-theory. Or if you're working with the row algebra themselves, then they're even isomorphic to each other. So that's an advantage of working with the row algebras, that in this case, any choice of maximal epsilon separated subset will give you isomorphic row algebras in the end. So therefore, to a certain extent, it's an invariant of the manifold and not of the subset that you choose of this discretization. Okay, now, why do we want bounded geometry? So first note that if we have any bounded operator on acting on L2 of x, then it will have uniformly bounded matrix entries, just by this short estimate here. The matrix entries are bounded from above by the operator norm of the operator T. But now the question is, what about the converse? Assume we have a band diagonal matrix and the entries are uniformly bounded. Then in general, it will not define a bounded linear operator, but only if we have bounded geometry. And that's just what this lemma says. Every band diagonal matrix over a space of bounded geometry, if this matrix has uniformly bounded entries, defines a bounded operator and hence lies in a uniform row algebra. So this is one of the reasons why I usually assume all spaces to have bounded geometry, because then at least the band diagonal stuff is completely understood. And as I already said, if the matrix is not band diagonal, then it is much harder to characterize when it is actually in the uniform row algebra. And now we are coming to the main definition of this talk, quasi-local operators. So we consider a bounded linear operator T acting on the square summable sequences on X, on L2 of X, and we call it quasi-local if we can find a function mu mapping the positive reals to the positive reals, with the only property that mu of r goes to 0 as r goes to infinity. So we don't have to demand here any sort of continuity of this function or whatever, just this limit property. And then we want that this estimate here holds, namely, so we have a vector v, and we fix a number r, and then we apply our operator t to the vector v, and then we compute its norm, but not the full norm of it, but we go only, so we leave out all the points in the neighborhood of the support of v. So note that we are working in small L2 of x. So the norm of a sequence is just the square sum of the entries of the sequence. And this norm here, where I have written x without r neighborhood of the support of v, just means take the square sum, but only over this z. So leave out a neighborhood of the original support of the vector. And we want that this, you can call it semi-norm, is bounded from above by mu of r times the original norm of v. Now, if you would allow this function mu to depend on the vector v, then this would be always true, right? Because the result t of v is a L2 sequence. So you can always find a function mu such that this is satisfied, but it will depend on your vector v. And so the important point here is that this function mu does not depend on the vector v. So this is some sort of, you give your operator, you somehow want that it somehow decays at infinity somehow suitably in a certain sense. And yeah, so for data, we call such a function the dominating function.
Excuse me, I ask a question.
Yeah, sure.
What is support of V?
So V is an L2 vector over X. So it's just all the points where the vector V is non-zero, all the points of X.
Okay,
So V is just an L2 sequence which is indexed over X.
okay, so this is like, okay, so typical vector will have like support in the whole X, but you're saying that
For example,
if a vector V is supported in some subset, then you want this decay property. Okay. Okay.
yes. I mean, imagine something like for the vector V, say a Dirac mass at a single point. Then you apply your operator T to it, and then the result will be supported somewhere. But this condition here means that somehow it is still, so the resulting vector is still supported close to your original point where your Dirac mass was living. And this is supported close to it is uniformly so in the sense that it's independent of the point that you consider to form this Dirac mass.
Okay, thank you.
Still, you will require here that V has a finite support.
Well, I mean, this also makes sense when what I've written down makes sense for all V. If the support is everything, so then the left-hand side is just zero. Then it's just obviously 2.
Okay, perfect.
So it makes sense for all V. So if you imagine T, so what I usually do is I imagine T in this case actually always as an infinite matrix indexed by the space X. So so basically if an operator is quasi-local, then it is in my imagination sort of band diagonal. So it's basically band diagonal up to an epsilon. So basically the stuff outside of the band is less than epsilon. And the further you go off the diagonal, so the bigger you make your band that you consider, the smaller the epsilon gets. That's somehow how I imagine quasi-local operators. Now we have the following basic facts about quasi-local operators, namely, if your operator has finite propagation, then it will be quasi-local, because you can just do the following naive choice of dominating function. Just let it be the operator norm of T up to the propagation of T, and from that point on, just define it to be 0. This will obviously satisfy this inequality here, because yeah, it's either it's the operator norm of T, then it's true by the definition of the operator norm, or it's 0, but the values of R where it is 0 are exactly the values where the left-hand side becomes 0 anyway. Because then you have taken out a neighborhood which is larger than the propagation of the operator. So finite propagation operators are obviously quasi-local. What you can also check is that the composition of quasi-local operators is again quasi-local. That's not completely obvious. One has to think for a minute or two about this. And what you can also prove is that the algebra of quasi-local operators is norm-closed. Or phrased differently, if you have a sequence of quasi-local operators converge in an operator norm, then the limit operator will also be quasi-local. That's also something that where you have to think about for 1 or 2 minutes to see that this is true. So that's not immediately completely obvious, maybe. But so this means that this algebra C star QL of X is a C star algebra. And since it contains the finite propagation operators, it will contain the uniform row algebra as a subalgebra. And the main question now that I want to pursue here is, when do we actually have equality? Because somehow a priori you might think, well, if I have a quasi-local operator, so let me go back to this defining slide here. If I have such a quasi-local operator, now I represent it as a matrix. Then I said, I'm thinking of this about something like it's band diagonal up to an epsilon. So the naive approach would be to say something like, well, then just take an epsilon, take this band, and cut the operator off at this band. So throw away everything which is far away from the band in order to actually define a band diagonal operator. And then if you make this band bigger and bigger, then you hope for that this converges to your original operator that you started with. So something, the naive idea would be just cutting quasi-local operators along the bands in a matrix representation to show that actually every quasi-local operator can be approximated in operator norm by finite propagation operators. But this naive idea completely fails. Really, it fails horribly, because the worst thing that can happen happens, namely that even on easy spaces like Z, it can happen that this cutoff procedure produces operators whose operator norm goes to infinity in this process. So basically, by cutting a quasi-local operator to bands, can actually enlarge arbitrarily its operator norm. And this even on easy spaces like Z. So this naive idea is just horribly wrong. So therefore, it's a valid question, well, what to do then? Because somehow in my mind, it should be true that this is always an equality somehow, at least up to 5 years ago. Maybe it was clear in my mind that this should be the case somehow.
Can I ask a question? Maybe.
Sure.
Maybe you go in that direction, but if we take a product of two elements from the two algebras, can we say anything about that product? So an element from the left, one from the right. Can we multiply them?
I mean, you can multiply them because these are algebras, so you of course end up with a quasi-local operator. You're probably maybe asking if the uniform row algebra is an ideal, but that's not the case, I would say. I mean, I've never really thought about this question, but I think if it would be an ideal, then the question that I've written down here would be much easier.
Okay.
Well, it contains the identity operator, so
Yes.
Oh,
Cannot be
yes,
an ideal.
right.
The multiplier, yeah, you cannot do anything with the multiplier stuff.
Yes, right. Maybe I should have mentioned this from the beginning. So the uniform row algebra is unital because the identity matrix is in it.
Okay.
Okay, so actually this question, whether these two algebras coincide, it was asked by John Rowe in the 90s. And then it took over 20 years to actually get even the first partial result on this direction. So it turned out to be an extremely hard question. Yeah, and then Spakula and Tikrishes, respectively Spakula and Jan, proved basically the best possible result that you can expect if you're familiar with coarse geometry. Namely, if as usual, you start with a proper metric space of bounded geometry. So that's the standard assumption in this field. And then the best possible result is that if X is property A, then you have equality. So property A, I don't want to define it here because it is actually not relevant for the rest of the talk, but I just want to say that it's an extremely general property. So in the sense that it was for a very long time an open problem to actually construct a space which does not have this property. So therefore one can say somehow for almost all spaces, because it's extremely hard to construct one which does not have this property, you have a positive answer to the question. And this is, as I said, if you're familiar with large scale geometry, this property A assumption is a natural one. But it was, as I said, the hard problem. It took more than 20 years to prove actually any such result. And we still don't know anything in the remaining case. So that's, as far as I know, completely open. So if X does not have property A, we just don't know what happens. Especially we don't know a single space where the answer is negative. So we don't know a single quasi-local operator which is not in the uniform row algebra. So that's currently a completely open question on this topic. We don't even have candidates as far as I know. So there are not even candidates of quasi-local operators where one hopes to prove that they are not in the uniform row algebra or something like this. So they're just, as far as I know, no ideas right now out there to somehow approach any of this. Okay, are there any questions up to now?
Yeah, I should have said, Nigel mentioned the identity, but it still could be the essential closure of some idea. So then it's a problem of essential closures of ideas. Who knows? But then property A, is it just a simple state, a lattice has property A for a good news?
You mean
Well,
lattice in
That's
what?
true. All lattices do have property A, right? So,
Okay.
You mean lattices in D group, so
you have to be very imaginative not to end up with a property A space.
okay. So if there are no questions right now, let me go. So this was basically what I meant by the first question that I wanted to address in this talk, namely how to characterize the operators in the uniform row algebra that you get, so that you get by forming this closure. I mean, of course, you can ask now yourself if this characterization by quasi-local operators suits you or not, or if you want to find some other characterization. I mean, you can also ask what would be favorable is there a characterization just by looking at the matrix entries? That would be also a nice answer, right? That you just have to look at the matrix entries of an operator, and then you can somehow tell from them if you're in the uniform row algebra or not. But as far as I know, there's just no answer to this currently. No answer which is true for every space X or something like this.
So you started the discussion saying that the row algebra is an invariant for metric spaces. Can we say the same for this quasi-local algebra?
Yes, I mean, the only information, I mean, you're just using the information of the metric space to construct this thing. So it is an invariant of the metric space. So if you have a bi-Lipschitz equivalence, then you will get isomorphisms of these star algebras. Actually, even more is true. So I don't have this at all on my slides, but these things are, to a certain extent, even quasi-isometry invariants of the space, or more generally coarse invariants. So in the sense that if you have two metric spaces which are quasi-isometric to each other, then the resulting row algebras will be isomorphic, or the resulting uniform row algebras will be Morita equivalent. And interestingly, one can also prove the converse under the assumption of property A. So if your two spaces have property A, and the uniform row algebras are Morita equivalent, then you can actually prove that your two spaces were Corsi equivalent that you started with. So it's basically these star algebras contain all the metric information up to quasi-isometry of the metric space. So it's something similar like you have a topological space and you look at the C0 functions of the space, then you have the same statement, right? So it's known as Gelfand duality. If C0 of X and C0 of Y are isomorphic, then X and Y are homeomorphic. And here you have the same for quasi-isometries. If the uniform row algebras are Morita equivalent, then the spaces will be quasi-isometric.
Wow.
So therefore, you captured a lot of the metric information. Basically, almost everything of the metric information is captured in these algebras. Interestingly, we have to assume property A for this to be true. So, and I think, again, nobody knows what happens if you drop this condition.
Thank you.
Okay, so then let me get to the second question for my talk, namely, what can we say about the resolvence of finite propagation operators? And so the basic definition that I need here is of a spectrally invariant subalgebra. So we have a C star algebra A, and we have a dense star algebra curly A in it, and we call it spectrally invariant if, where for all operators in your subalgebra, the spectrum, if you compute it in curly A, is the same as the spectrum if you would compute it in the C star algebra. So it just means that, spectrally invariant. So operators have the same spectrum. So you don't have to go to the C star algebra to compute the spectrum. So one reason why I am interested in spectral invariant stuff is because they have the same K-theory. So finding a nice spectral invariant subalgebra means you can usually get a much better understanding of the K-theory. And yeah, now that's the now goes back to this motivation. So the Hamiltonians that we considered at the beginning, so the interacting particles, since they have finite propagation, means that the resolvents will be elements in every spectral invariant subalgebra. So therefore, if you find a spectral invariant subalgebra, then you immediately get information about the resolvents of finite propagation operators. So this is
sorry,
something
can I
that
ask
you,
something
yes.
possibly technical about this spectral invariant. So I thought you need something like strong spectral invariance, which is that you have even after tensoring by some matrix algebra, you continue to have this property. So this is for the purposes of the case theory.
Yes,
Is that important?
I mean, you're right. I mean, I have neglected this more technical effect here. So usually the actual definition is, as you said, you have to also to pass to matrix algebras, and usually you also demand that this dense subalgebra is actually a Frege algebra with a family of submultiplicative seminorms or something like this. So, but I've just I'm ignoring all these technical issues because
so it's not a special property of the uniform row algebra that you automatically get these things. You still have to check.
Yes, you still have to check this. It's just that I'm ignoring it for simplicity of the talk. But yes, you have to also pass to matrix algebras. Yes, you're right.
Okay, yeah, thank you.
Okay, so and that's what we are going to do now. Find a nice spectrally invariant subalgebra of the uniform row algebra. So how to do this? And as I already said, we will again use the notion of quasi-local operators. Namely, we define the following family of norms. So T is a finite propagation operator, and we fix the natural number n. And then we do the following. So we consider, so we have here mu T of R. So this is the smallest possible choice of a dominating function for the operator T. So note that I, maybe if I go back here, so here, so this function mu that I've written down here that you can choose if T has finite propagation, that's just one possible choice for dominating function, but usually it's not the smallest possible choice of function mu. So now for this definition, in order for this to really make it a nice norm, so you look at the smallest possible choice of dominating function, and then you demand that it is bounded from above by the polynomial, by 1 over a polynomial in R. So you want that the dominating function decays like a polynomial. And then you just, and so the actual value of the norm is then the infimum of all these constants d that you can put here on the right-hand side of this estimate. But this just means that if your operator has a finite such norm, then it means its dominating function decays polynomially as a polynomial of degree n or faster. And then we just define C star polynomial of x to be the closure of all finite propagation operators in the resulting family of norms. So you throw in the operator norm and for every n, these things that we have defined now. So that's the family of norms. And so C star polynomial of x will be a Frege algebra. And as I've already said, having finite such norm means your dominating function decays polynomially. Therefore, an operator in this algebra C star polynomial of x, so being in this algebra, in this Frege algebra, means that you have a super polynomially decaying dominating function. Because for every n, your norm must be bounded. So for every n, your dominating function decays like a polynomial of this degree. And now, of course, the main technical lemma is that this thing is spectrally invariant. And this does not have any assumptions on x, actually. So for every metric space, as far as I remember. So especially no property A assumption or whatsoever. And I also think no bounded geometry assumption even. So that's a spectral invariant subalgebra that you can always define, which is very nice because this means that if you have a finite propagation operator, and you consider a resolvent of it, then this resolvent will always lie in this Frege subalgebra. So you always have information about the resolvent, which is more than just it's also in the uniform row algebra. And one nice way of how one can apply this is, so at the beginning I was talking about the very basic example of the lattice Z to the N and R to the N. And for such nice lattices, this means a lot, this lemma, that the subalgebra is spectral invariant. More generally, we say that the metric space of Pound geometry has polynomial growth if the number of points in the ball is just asymptotically like a polynomial in the radius. For example, as I said, so the lattice Z to the N has polynomial growth. So there was a question in the chat, if an algebra is closed with respect to holomorphic functional calculus, if it is then also spectrally invariant. Actually, if you write down the correct definition, then I think this is equivalent. So if you do this, it's a Frege algebra, and you also pass to matrix algebra. So being closed on the holomorphic functional calculus is this basically the same as being spectrally closed. It's basically the same as being inverse closed. So meaning that if your operator is invertible in the C-star algebra, then the inverse already lives in the subalgebra. So these notions are basically equivalent to each other.
What does mean basically equivalent? What does basic stand for?
I think there were some very technical requirements, something like your Frege. So the subalgebra should be a Frege algebra in some set of semi-norms. It should contain the original C-star norm. They should be submultiplicative or something like having an open set of invertibles or something like this. So there were some technical assumptions on this Frege structure somehow. But yeah, so but if these technical assumptions are satisfied, then the notions are equivalent.
Okay, thank you.
Okay, and the lemma that I have written down here is now, so that's actually, I was talking about, so when I basically answered the first question, namely, how can we characterize if an operator is in the uniform row algebra? Then I gave you this characterization via quasi-local operators, at least if you're in the property A case. And then I said, well, maybe you actually wanted something else, namely some sort of characterization with respect to the matrix entries, something like you want to look at the matrix entries of your operator, see how they decay, and then you want to know if you are in the uniform row algebra or not. And I told you that I can't give you the answer to this because as far as I know, this is not really known. It's least not in an if and only if characterization. But if you have polynomial growth, then you get an if and only if characterization for this spectrally invariant subalgebra. And it is this characterization that you see here, namely, so if your space is polynomial growth, then an operator T is in this spectrally invariant subalgebra if and only if the following condition is satisfied on its matrix entries, namely that they are summable along each column and along each row, even if you put polynomial weights to them. So this is this times the distance from x to y to decay. So this means that basically if you look at the matrix of your operator T, then the decay of the entries of the diagonal is basically it's summable, and even with polynomial weights, it's summable. And this then will be an if and only if characterization. Of course, the restriction to spaces of polynomial growth, depending on what you want to do, might be a hard restriction for you, or it might be okay for you. But if you just like to work the lattice Z to the N, then this is perfectly fine for you. And especially what I said, if you have a finite propagation operator, then its resolvence will satisfy this condition here in the polynomial growth case. Okay. Thank you.
Thank you very much. Very clear talk. Any questions or comments for Alexander?
One question going back to the previous slide. Oh, maybe there are people who raise hands.
Not yet. Not that I see.
So the focus is on the polynomial growth. If you try exponential growth, why is that this one seems natural and the exponential not?
So I have actually tried exponential growth, because I mean, you mean if you would what do you mean with exponential growth? So that the dominating function should be exponentially decaying.
Yes.
I assume that you want to prove that this thing is spectrally closed.
And with the exponent,
spectrally invariant. So
exponent in the interval, open interval 0, 1 or maybe.
Yes, so I have tried this, and I have tried many variations of this, because if you could prove this, so if you could prove that some sort of exponential decay gives you a spectral invariant subalgebra, then immediately the whole question about the Novikov conjecture here would be much, much easier. So I have actually tried this and I just failed, and I think it's even wrong. So if whatever kind of exponential decay you write down, I think it will not be exponentially closed.
Yeah, you can build examples using Fourier theory just on the line, on the integers, where you'll see that if you fix a rate of exponential decay, you won't get a spectrally closed algebra.
Of the union of all of them. So this polynomial growth has something to do with smooth functions on the circle in the easiest case.
That's right.
And you could replace the circle by real analytic functions, which means those functions where I suppose in this case it's a Laurent series, converges on some little strip around the unit circle. And if you allow the strip to be as small as you like, this would again be holomorphically closed. And indeed, if you use the right concepts, then this would be an allowed subalgebra. It's not a Fréchet algebra because you're taking an inductive limit of Banach algebras. It would be a Born logical algebra, but that is okay. But if you want to fix the radius, then it would not work.
But so I think what you're saying is that, so since you're doing the limit the other way around, so basically you're doing a union, right? So this means that you would have an exponential decay with arbitrarily bad exponent.
Yes,
somehow,
arbitrarily
right?
small, yes.
Yes, and that's the problem. Okay, maybe this is spectrally invariant, okay, but then you couldn't prove much more from this than here in the polynomial growth case.
That's
because
right,
because if you have any space X which has exponential growth, then it has this exponential growth like a hyperbolic space with respect to a fixed constant. But since in your subalgebra you have arbitrarily bad constants, this does not help you to prove any lemma from this then in the end. So then basically the only thing that you have managed is to go from super polynomial to sub-exponential, which is a very, very small distinction.
Yes, indeed. But, well, that I'm not quite certain what exactly you would know in these Anderson localization situations. There is some exponential growth, but
yeah, that's it.
The constant is also small, or could be. So you don't know anything about the lower bound for this constant, do you?
So the lower bound usually, no, we do know it's the localization length that we make plots. But I should mention that, for example, this grow condition written here down in the mobility gap will not hold unless you average over the disorder. So that
is right. That's another complication.
That's a complication. You have to put the average over a random variable to get such bounds.
Alexander, I think it's related to what we're hearing in the physics discussion here. But did you think about algebras which are bigger than Rowe's algebra? Let's just say on the integers. So instead of trying to understand what's in the Rowe-Sister algebra, build an algebra where the decay is not quite good enough to be in the Rowe algebra. So under Fourier transform, it would correspond to considering not continuous functions, but functions just satisfying some Sobolev condition. I wonder if you thought about that from this coarse geometric point of view.
Actually, no, I've never tried to pursue this idea. I mean, I have worked with Sobolev functions, but in order to get smoothing operators and stuff like this, so again, the other direction, so making the algebra small, not large.
Yeah, that's certainly what we usually do.
But it's actually something that I was thinking about this idea of making the algebra larger. So it's something like this problem with the counterexamples to the surjectivity of Coase-Baum-Kohn. I was thinking something like, well, what if you do not map into the uniform or the row algebra to quasi-local operators? So go a bit further, because then I think the context. So I have went through your construction of the counterexample, so the construction of these two traces which find this thing which is not hit by the assembly map. And the construction of the non-trivial one of these things breaks down if you go to quasi-local operators. So the trace does not exist anymore. So I have ever wondered if maybe the counterexamples can disappear if you pass to the quasi-local operators.
Interesting.
Because the trace does not make sense anymore. It's really, the reason why it does not make sense anymore is really this distinction that you pass to. I mean, it's really a fundamental thing that the trace fails to be there.
Mm-hmm. Yeah, it's very interesting. I have not thought about that.
But you said you didn't know whether there are different C-star algebras in that case. So the counterexample that you mentioned, you don't know whether the quasi-local C-star algebra is different from the uniform row C-star algebra in that case.
Yes, right.
It's just
so
that you cannot write down the construction anymore, so you know really nothing about it. It's very subtle.
Yeah, so the thing is that everything breaks down in this case. So we don't know if the algebras are different, but even if we could write down any quasi-local projection which is not in the row algebra, the proof of the non-surjectivity breaks down.
Any other questions?
Okay, 1150. I have you haven't said anything about the K theory. How wild can it be, or how trivial can it be?
Oh yes, so let me say, if you work with the usual row algebra, so where you have Hilbert spaces and locally compact as an additional condition, then the K theory is computable in the sense that, for example, Z to the N then just has Z or Z plus Z as a K theory, because you actually have a suspension isomorphism by taking product with R, respectively product with Z. But the uniform row algebra has an extremely huge K theory. So even in the case of Z, I think it's uncountably generated as an abelian group.
Mm-hmm.
Because then you can start to distinguish somehow different growth rates, whatever this means, but so it stems from the fact that you have uncountably many different growth rates somehow that you can pack together in things. So it's really huge from this perspective.
Okay, so if we work with this quasi-local C-star algebra, then it's the same situation.
For Z, yes, they're the same C-star algebra in that case.
So
because Z has property A, Z to the N also. But I wanted to comment that for the integers, this huge K theory actually has a physical reason why it has to exist. That's because this uniform row algebra has lots of traces, and it contains many things. If you have a one-dimensional quasi-crystal, then you can embed its C-star algebra into the C-star algebra into this uniform row C-star algebra, because you can write this row C-star algebra as a cross product of functions on the Stone-Čech compactification of Z, cross product with the translation action of Z. If you have any Z action on a compact Hausdorff space, you can look at one orbit and restrict your functions to this orbit. You get bounded functions, which means you end up in this Stone-Čech compactification. And if there's an invariant measure on your on the space on which Z is acting, then there's a good chance this would extend to this Stone-Čech compactification and give you a trace there. So this has lots of traces, and in nice examples you can see that these interesting traces exist still in the uniform row algebra, and then they have to be non-trivial maps on the K-theory. And in these one-dimensional quasi-crystals, you can have interesting projections which are separated by, well, some traces, like for instance these irrational rotation algebra things. And so in the uniform row algebra, these things survive in the K0 of this uniform row algebra, but they go away in the row algebra itself because that has trivial K0, and in fact it has no bounded traces.
Maybe it's worth saying that when John invented these things back in the middle of the 1980s, it was exactly to carry these traces. The traces came first, and then John built the algebras around them.
Yes, actually, the uniform row algebra was the first thing that he invented. Only afterwards, he switched to the row algebra.
If there are no further comments, we have the rare privilege of a 5-minute break, which I propose we seize. I'm anxious to stand up. So thank you very much, Alexander, for your wonderful talk. We shall